Hi, today we need to talk about table F. This table can be found among other stuff in your set of reference tables, and this table represents solubility guidelines for aqueous solutions. So we know that majority of ionic compounds will dissolve in water because water pulls on those positively and negatively charged ions, tearing them apart and separating ions. However, there are several ionic compounds in which ions are so strongly attached to each other that even water cannot pull them apart. No matter how much we stir, no matter how much solvent we decided to use for it, increased temperature or anything else, those compounds will remain stubbornly in crystallic form, and eventually they will precipitate to the bottom of the test tube. Table F helps us to identify those insoluble compounds, but to identify them with the help of this table, you need to be able to read this particular table. You can see that this table is split into two halves. The left half of this table represents ions that usually form ionic compounds that are soluble in water. And the right half of this table represent those ions that usually form insoluble compounds in the water. Now, let's learn how to read this table. Let's first look at the left half of the table F. Okay, ions that form soluble compounds. All these ions that we see in the left column represent ions that usually are part of soluble compounds that will be very nicely dissolving in water, forming aqueous solutions, unless they are with the exceptions. Okay, let's look at some examples to see how it works. Here are a few ionic compounds. So let's start with this one, sodium chloride. Sodium chloride is our table salt, and we all know that it dissolves very nicely in water. We've seen it many times in our kitchen. But let's see how this table works for it. Well, sodium as an ion forms, according to this table, soluble compound. So any compound that includes a sodium ion in it will be a soluble compound. There are no exceptions to the rule. Anything that includes sodium as an ion will be a soluble compound. We will represent it by putting a subscript of AQ in the tiny parentheses next to the compound of sodium chloride. Okay, let's look at another example. Lead to bromide. Okay, if we look at the table, we will see that the bromide usually forms a soluble ionic compounds. So let's say calcium bromide would be a soluble compound. We would mark it as aqueous solution because bromides normally, majority of bromides are soluble compounds. However, if this bromide ion happen to be standing next to one of the exceptions, silver, lead, or mercury, then that compound will be insoluble. So our example of lead 2 bromide is actually going to be insoluble compound. So we will put tiny s next to it to represent that this compound is insoluble. It's going to stay solid no matter how much we stir, no matter how much temperature we increase, and it's going to be a solid no matter what, and eventually will precipitate to the bottom of the test tube. Now let's look at two sulfates, ammonium sulfate and barium sulfate. What about them? Are they soluble or insoluble in water? Well, if we check our table, we will see that sulfate usually forms ionic compounds that are soluble in water, unless it's with one of the exceptions. So we're checking the exception box, and ammonium ion is not one of the exceptions. That means that our ammonium sulfate is going to be a soluble compound. It will dissolve in water just fine and will form an aqueous solution. However, if we look at our exception box when we are analyzing barium sulfate, we will see that the barium is actually one of the exceptions. When sulfate is paired with the barium, instead of forming a soluble compound as we expected from a sulfate, it will form insoluble compound that will form precipitate at the bottom of the jar or of the test tube. Sometimes instead of putting the letter S as a representation that the compound is insoluble like we did over here, we with the same success can use the letters PPT. PPT stands for precipitate. It means that these are going to be insoluble compound that will remain solid, whether we're putting a tiny s or whether we're putting a PPT in parentheses next to a compound. It means the same thing. This particular compound is insoluble in water, will stay crystallic no matter what we do to it. Now let's look at calcium chlorate. This compound over here, chlorate ion, is clearly here on the table of soluble ionic ions, that ions form soluble compound, and you can see that chlorate doesn't have any exceptions. So any ionic compounds that includes chlorate in its structure will be a soluble compound. So we can bravely put AQ next to this compound. Now let's consider silver chlorate. Okay, normally chlorides form soluble compounds. Majority of chlorides are soluble. However, when they are seen with their exceptions, and one of them happened to be silver, they become insoluble. So our silver chloride happened to be a solid and would not form an aqueous solution. Those ions of silver and chloride will not dissociate in water. Now let's talk about right part of table F. This time tables are turned because the ions that you see in the left part, in the left column of this table, are forming insoluble compounds. It means that majority of carbonates are insoluble. Majority of chromates are insoluble, phosphates, sulfites, hydroxide. Majority of ions that contain those ions are going to be solid. They're going to stay crystallic and would not dissolve in water, not forming aqueous solution. However, when those ions happen to be standing next to the exceptions, then the ionic compounds that are formed by this ion and that exception would be a soluble compound. Let's look at some examples. Okay, here I wrote two examples that contain each of those compounds or each of those ions that we're talking about. So here are a couple of carbonates, and normally majority of carbonates are forming insoluble compounds. So the moment we see carbonate in any compound, we assume that it's insoluble. It's going to be solid and it will not be dissolved in aqueous solution. Then we go and check if by any chance the carbonate ion happen to be accompanied by one of the exceptions. And look at this. All metals from group number 1 happen to be that exception. So what can we say about our calcium carbonate and lithium carbonate? We can say that calcium carbonate is going to be a solid. What is expected from the carbonates? Carbonates are usually insoluble. They remain solid no matter what. But lithium happens to be element from group number 1, meaning that this is the exception that changes our carbonates into a soluble compound. So over here we have a compound that will form an aqueous solution. If we dump a bunch of crystals of lithium carbonate into water, that they dissolve and disappear. Okay, how about this? Iron 3 chromate and magnesium chromate. Okay, chromate is right here, and now we need to check. Majority of chromates will be insoluble. So this is why we can actually decide on the iron chromate to be the PPT, to form that insoluble compound. While magnesium chromate happens to be one of the exceptions. So when our chromate shows up in a company of magnesium, that compound is going to be soluble. It will form aqueous solution if we put those crystals into the water. Let's look at the phosphate. Phosphate ion, that is, forms insoluble compounds. But when it is seen with the ammonium or any of the metals from group number 1, that story changes. Our insoluble phosphates become actually soluble compounds. So ammonium phosphate here is going to be aqueous solution, while aluminum phosphate is going to stay solid, because aluminum is not an exception to the rule. We do not see it among the exceptions, so phosphate of aluminum is going to be a solid compound that would not dissolve in water. Let's look at the sulfides. Barium sulfide. Sulfides usually insoluble compounds, unless they are with the exception. Barium is element from group number 2, so this line does not apply to it, and barium is not ammonium ion, so in this regard we believe that barium sulfate is going to be a solid even if we will try to dissolve it. However, ammonium ion happens to be one of those exceptions, so when we see our sulfide ion showing up in the company of ammonium ion here, then we know we're talking about a compound that can form an aqueous solution. The last one, hydroxide. Hydroxides usually insoluble, but when they are with their exceptions, like for example in this compound, they become soluble. Iron 2 hydroxide that I have to the left, right here, have another compound. Iron is not an exception. We do not see it among the hydroxide exceptions. It's not in this box, meaning that our hydroxide will be solid in here. Okay, now I want you to stop video and create a table like this in your notebook or on a piece of paper, because I'm about to ask you to write the formulas of the compounds in these boxes and identify them as soluble or insoluble compounds. I'll help you with the first 2 or 3, and then I will ask you to do it on your own. So let's see, over here we can see that we have lead with a charge +2 and chloride ion with a charge -1. Well, as far as we remember that all ionic compounds supposed to be electronically neutral, correct formula of lead 2 chloride is supposed to have 2 chloride ions, otherwise it's not electronically neutral. Okay, correct formula is written. Now let's see if this qualifies as soluble or insoluble compound. Chlorides usually form soluble compounds unless they are with the exception, and lead happens to be one of those exceptions, meaning that this compound will be deemed to be a solid. Okay, let's do another one. How about this potassium chloride? Potassium charge +1, chloride charge -1. We don't need to do anything regarding making it electronically neutral because it already is. And now let's see, chlorides are usually soluble compounds, and we can see potassium next to the chloride, which means that since potassium is not an exception, then this compound will be forming aqueous solution if we will try to dissolve it in water. Okay, let's look at barium chloride. How about this one? Barium, oops, it's not working the way I want it. Okay, barium chloride. Well, first things first, let's write the formula correctly. Barium has a charge of +2, chloride has a charge of -1. Two chloride ions are needed to have this formula to be electronically neutral. Now, let's analyze our chlorides, usually soluble. Barium is not an exception. In our left part of the equation, we can say that this is going to be an aqueous solution. Now, please pause this video and continue to fill up this table on your own. Fill up the entire table and then compare. Compare two things. How correctly written your formula is, if your formula of the compound electronically neutral. That's one question. And secondly, compare if that compound that you've written can be identified as soluble or an insoluble compound. Here are the answers, so please check, compare that with your own table and see where some mistakes might have crept in, or maybe everything was perfect. That would be great.